Section each, 18,000 tons of supplies every single day. That was the minimum logistical floor required to sustain the Allied Liberation Force in Normandy during the initial phase of the invasion. But German High Command knew this too. Their entire defensive strategy relied on a simple, brutal calculation. Deny the Allies a deep water port, and the invasion force would wither on the vine within 48 hours. The greatest amphibious assault in history faced a mathematical dead end before it even began. Now, let's open the operational records and analyze the systems that defined this campaign. When we analyze the strategic map of Senkyu Tao-Si Jushi, we see a massive disconnect between tactical objectives and logistical realities. The Allied High Command, specifically the planners at SHAEF Supreme Headquarters Allied Expeditionary Force, understood that getting boots on the sand was only the preamble. The true operation was sustainment. A modern mechanized army is a voracious consumer. Its operational tempo is dictated entirely by its supply chain. For the Allies to push inland, they needed a continuous, unbroken river of fuel, ammunition, and spare parts flowing across the English Channel. However, the German Atlantic Wall was not just a line of bunkers. It was a system designed to weaponize logistics against the invader. Field Marshal Rommel and the German staff had heavily fortified every major port from Cherbourg to Calais. They reasoned that while an enemy might land on a beach, they could not support a heavy mechanized advance without the cranes, docks, and deep water berths of a major harbor. The disastrous Dibe raid of Senkyu Hakatsuduni had already proven this hypothesis with bloody clarity. Attempting to seize a well-defended port head-on was suicidal. Furthermore, even if a port were captured, the Germans were prepared to systematically destroy its infrastructure, rendering it useless for months. This created the port paradox. The Allies needed heavy armor and vast quantities of fuel to capture a port, but they needed a port to offload that armor and fuel in the first place. The beaches of Normandy, Omaha, Utah, Gold, Juno, and Sword offered a tactical surprise, but they were a logistical nightmare. They were flat, exposed to the notorious weather of the Channel, and lacked any infrastructure to handle heavy cargo, relying solely on logistics over the shore. Ferrying supplies via landing craft directly to the sand would create an immediate bottleneck. The throughput capacity of beach landings was mathematically insufficient to match the projected burn rate of the invasion force. With German panzer divisions held in reserve, ready to counterattack, any interruption in the supply chain would result in the beachhead being pushed back into the sea. The planners faced a binary choice: capture a port immediately, which was impossible, or bring the port with them. Section E. The solution was an engineering audacity that defied conventional naval doctrine. Since the operational environment denied the Allies a natural harbor, they decided to manufacture one in Britain and tow it across the Channel. This was the genesis of the Mulberry harbours. The concept originated from a specific directive by Winston Churchill, who famously wrote regarding the idea of floating piers. Don't argue the matter. The difficulties will argue for themselves. This memo shifted the invasion planning from a purely tactical military operation to a massive industrial construction project. When we examine the blueprints for Operation Overlord, we see that the logistical plan hinged on two distinct, massive engineering systems designed to bypass the German chokehold on French ports. The first component was the artificial harbor system. The plan called for two complete ports: Mulberry A for the American sector at Omaha Beach, and Mulberry B, nicknamed Port Winston, for the British and Canadian sectors at Gold Beach. These were not mere floating jetties. They were fully functional port complexes. The specifications required them to handle the tonnage of a mid-sized city's commercial hub, protecting transport ships from the turbulent channel waters, while providing roadways for trucks to drive directly from the cargo hold to the shore. The scale of this fabrication effort was staggering. It required the construction of massive concrete casings, floating roadways, and breakwaters at sites scattered across the entire southern coast of England, all under the strictest secrecy. The second component addressed the lifeblood of the mechanized army: fuel. The planners calculated that the invasion force would consume fuel at a rate that traditional tanker tow truck transfer methods could not sustain. A jerry-can brigade would simply be too slow and too vulnerable to interdiction. The answer was PLUTO pipelines under the ocean. The concept was to lay continuous, flexible, high-pressure petroleum lines from the Isle of Wight directly to the French coast. This system was designed to eliminate the need for dangerous ship-to-shore fuel transfers, pumping petrol directly into the operational theater's supply depots. Together, Mulberry and PLUTO formed a radical, logistics-over-the-shore strategy. The operational timeline was tight and unforgiving. The plan dictated that within days of D-Day, tugboats would haul these massive structures, some weighing as much as luxen tons across the open water. Once assembled, they were projected to offload each many centons of supplies per day collectively. However, when we analyze the risk assessment of this plan, we see a dangerous reliance on ideal variables. The planners assumed manageable weather conditions during the installation phase. They operated on the assumption that the complex towing operations would not be disrupted by enemy E-boats or the unpredictable channel currents. Furthermore, the entire logistics timetable was predicated on these artificial systems, functioning at peak capacity immediately upon arrival. There was no redundancy. If the Mulberries failed to anchor, or if the pipelines fractured, the invasion force would be stranded with only days of supplies, facing a counterattacking enemy on established ground. The plan was a triumph of imagination, but it was about to be tested by the brutal physics of the English Channel. Section N. To understand how the Allies intended to cheat geography, we must deconstruct the specific technologies utilized. When we analyze the Mulberry and PLUTO projects, we are not looking at standard military infrastructure. We are looking at a localized industrial revolution, modularized and prepared for export. The engineering specifications for these systems reveal a complexity that rivaled the Manhattan Project in terms of resource allocation and technical innovation. The Mulberry system was less of a single structure and more of an ecosystem of interlocking components, each designed to mitigate a specific variable of the hostile channel environment. At the outer perimeter lay the bombardons, massive cruciform steel floats anchored to break the initial force of the waves. Behind them lay the Phoenix caissons. These were the titans of the Operation Hollow, reinforced concrete skyscrapers, some as long as knee-thick feet, and weighing luxen tons. The logistical brilliance here lay in their dual nature. They were designed to float for transport and then sink on command. Engineers equipped them with seacocks, valves that, once opened, would flood the internal chambers, grounding the structure on the seabed to form a solid breakwater. This required precise calculation. If a caisson was sunk at the wrong angle or on an uneven patch of seabed, the structural stress could crack the concrete spine, rendering the breakwater useless. Inside this artificial calm, the whale roadways formed the connective tissue between ship and shore. This was the specific engineering answer to the tide problem. The Normandy coast experiences a tidal range of over 90 feet. A fixed pier was operationally non-viable. At low tide, it would be high and dry. At high tide, it might be submerged. The solution was the spud pierhead, a platform that functioned like a jack-up rig. It stood on 4 steel legs resting on the seafloor, but the platform itself could slide up and down with the tide, remaining perfectly level. Connected to this were the flexible whale bridge spans, supported by beetle pontoons. These bridges were designed to articulate bending and flexing with the movement of the ocean without snapping, allowing a continuous stream of trucks to drive off Liberty ships and onto French soil at 90 miles per hour. Simultaneously, the fuel problem was being addressed through a radical reimagining of submarine cable technology. Operation PLUTO PPA lines under the ocean rejected the standard rigid pipes used in the oil industry, which required time-consuming welding and laying procedures. Instead, engineers adapted the manufacturing process of subsea telegraph cables. The Hayes cable was a 3-inch hollow lead pipe, reinforced with steel tape and armored wire. It was flexible enough to be coiled, but strong enough to withstand internal pressures of Sengo Hyakheho Inji Maipon. To deploy this, the Allies utilized the Kanon's gigantic floating drums, known as HMS Kanon drums, which were 100 feet in diameter. The logistical elegance of PLUTO was its deployability. A tugboat could simply tow a rotating drum across the channel, unspooling miles of fuel line in a single trip, invisible to German reconnaissance aircraft. However, when we map the data of this construction effort, we expose the massive hidden cost of these enablers. The logistical footprint required to build the logistics system was itself a strain on the British war economy. The Phoenix caissons alone consumed over lei tons of concrete and sen tons of steel. This demand was so high that it forced a slowdown in the construction of airfields and air raid shelters across the UK. The enablers were competing for resources with the very combat units they were designed to support. The project required a workforce of over 100 men, pulling labor from other critical industries. Furthermore, the complexity of the system introduced a fragility that often goes unnoticed in general histories. The Mulberry design relied on tight tolerances. The whale roadways required specific sea states to couple correctly. The PLUTO lines, while flexible, were susceptible to abrasion on the rocky seabed. We see here a classic systems trade-off to achieve high throughput capacity. The Allies built a system of immense high-tech complexity, thereby increasing the maintenance burden to band. They had built a Formula One car to drive through a mud pit. The technology was impressive, but it operated on the assumption that the environment would cooperate long enough for the system to take root. As the invasion fleet set sail, these millions of tons of concrete and steel were put to the ultimate test, not just against the Germans, but against the Atlantic Ocean itself. Section 7. By D-Day plus Juni, Senkyu Haksur Juyo, Nen, Rukagats, Duhatsni. The logistical miracle appeared to be a fait accompli. The tugboats had done their work. The Phoenix caissons were lined up off the French coast like the walls of a flooded fortress. The whale roadways were undulating with the rhythm of the swell, carrying a steady stream of Sherman tanks and trucks. Logistics planners were celebrating a triumph of capacity. The daily tonnage was climbing toward the target of Ichimenni tons per port. The system was seemingly beating the variables. But on June the variables fought back. A meteorological anomaly, the worst channel storm in 40 years, slammed into the Normandy coast. This was the ultimate stress test for the engineered systems, creating a 3-day period where the laws of physics collided violently with the laws of supply and demand. When we autopsy the destruction of the storm, we uncover a critical failure in the system's integration. The damage was not uniform. It was a tale of two harbors, and the difference lay in the adherence to logistical doctrine. At Mulberry, the American harbor; at Omaha, the destruction was total. When we analyze the failure reports, we see that the primary cause was not just the wave height, but the bombardments, the floating steel breakwaters designed to be the first line of defense. The engineering specs dictated that these massive steel crosses be anchored at precise depths to dampen the swell. However, under the ferocity of the gale, the mooring cables snapped. The enabler instantly turned into a wrecking ball. The free-floating bombardments were driven downwind, crashing directly into the concrete Phoenix caissons and the delicate whale roadways. We see a cascading systems failure. The outer shield destroyed the inner infrastructure. Furthermore, operational records indicate that the American logistical teams, under immense pressure to increase throughput for the stalled advance inland, had cut corners on the installation. They had spaced the caissons too far apart to widen the harbor mouth for faster ship entry. And crucially, they had failed to sand in the Phoenixes correctly. The scouring action of the current under the unsealed caissons caused them to crack their backs and disintegrate. Conversely, Mulberry B, the British harbor at Gold, survived. The autopsy reveals why. Stricter adherence to the engineering manual. The British engineers had lashed their caissons more tightly and secured the anchors into the seabed with greater redundancy. While damaged, Port Winston remained operational. The immediate result was a catastrophic drop in logistical capacity. On June Juhat, the supply flow was nearing peak efficiency. By June, the American port was a twisted ruin of scrap metal, officially abandoned. The British port was operating at a fraction of its potential. Now, let's look at the data graph for this week. It is terrifying. The demand curve was spiking vertically. The Allied armies were engaged in the high-intensity attrition warfare of the hedgerows. A single armored division in combat consumes up to WWII tons of supplies a day. With two armies fighting for their lives, the consumption rate was relentless. The capacity curve, however, had flatlined. The system had collapsed. But this autopsy reveals a surprising paradox in the data. While the high-tech billion-dollar Mulberry system failed at Omaha, the supply tonnage did not drop to zero. In fact, after a brief dip, it began to rise again without the harbor. How? The failure of the perfect system forced a reversion to a brute force system. Desperate to feed the guns, the American logistical commanders authorized the LST's landing ship, tank, to do exactly what naval doctrine advised against: ram the beach at high speed. They utilized the drying out method, driving the massive ships onto the sand at high tide, waiting for the tide to recede, offloading directly onto the dry beach, and floating away on the next high tide. This was dangerous. It risked breaking the keels of invaluable transport ships. It was inefficient in terms of turnaround time, but structurally, it was robust. It removed the fragile middleman, the floating roadways, and relied on the simple reliability of the tide in the hull. Meanwhile, the PLUTO system was also suffering its own operational crisis. The early attempts to lay the HAIS cable were plagued by failures. The pumps lacked sufficient pressure to push the fuel the full distance, and the coupling joints, designed in laboratories, were fracturing in the chaotic reality of the Channel seabed. For weeks, the sophisticated pipeline contributed almost nothing to the fuel stocks. The jerry can, the very inefficiency PLUTO was designed to replace, remained the primary method of fuel delivery, moved by hand from ship to shore in a human chain of labor. The system's autopsy of the Great Storm teaches us a vital lesson about logistical fragility. The Mulberry harbors were a marvel of efficiency designed to maximize throughput under specific conditions, but they lacked resilience. When the environment exceeded the design parameters, the complex system shattered. The crude method of beaching ships, while less efficient on paper, possessed the resilience to survive the chaos. By the end of June, the logistics over-the-shore tonnage at the American sector without a Mulberry actually exceeded the tonnage at the British sector with its functional Mulberry. The data proves that while the engineering marvels grabbed the headlines, it was the improvisation and redundancy of the supply chain that actually saved the Army from starvation. The miracle wasn't the concrete port. It was the realization that the port was optional if you were willing to break the rules of naval safety. Section Go. So what is the verdict? When we weigh the logistics miracle against the cold hard data of the campaign, the results are surprisingly ambiguous. If we judge Operation PLUTO and the Mulberry harbors solely by their initial performance metrics, they hovered dangerously close to failure. Mulberry A was a total loss within 2 weeks. PLUTO did not pump a significant drop of fuel until the breakout from Normandy was effectively over. During the critical first months, the Allied war machine ran on fuel landed by ship and poured from simple jerry cans. The technology arrived late to its own party. However, viewing these systems merely as delivery mechanisms is a fundamental error in analysis. Their true value wasn't in the tonnage they moved during the first week. It was in the strategic freedom they bought for the planners months before D-Day. The existence of the Mulberry concept was the key that unlocked the map. Without the promise of an artificial harbor, Allied commanders would have been forced to attack a fortified port like Cherbourg or Calais, directly a predictable move that the Germans were fully prepared to crush. The engineering solution allowed Eisenhower to choose a landing site that had no logistical business being a landing site. It broke the German defensive algorithm. Field Marshal Rommel looked at the map of Normandy, saw no ports, and assumed, logically, that no sustained invasion could happen there. The Mulberries allowed the Allies to weaponize that assumption. Furthermore, while Mulberry A failed, Port Winston Mulberry B, at Aromanches, served for 10 months. Landing the 10 million men and Gujuman vehicles. It provided the heavy lift capacity for the specialized equipment that simply couldn't be beached. And while Pluto missed the opening act, it became indispensable during the finale. As the Allied armies raced toward the Rhine, stretching their supply lines to the breaking point, the pipelines eventually functioning perfectly pumped over fax-to-Juni million gallons of fuel, relieving the immense pressure on the trucking convoys known as the Red Ball Express. The ultimate lesson of the D-Day supply miracle is a warning against the silver bullet fallacy in systems engineering. The Allies built a technological marvel, assuming that engineering precision could override environmental chaos. They were wrong. The storm proved that complex, tightly coupled systems are fragile. What actually saved the invasion was redundancy. The system worked because it was a hybrid. It had the high-tech efficiency of the Mulberries, but it was backed up by the low-tech, brute force resilience of LSTs, ramming the beach in human chains, passing fuel cans. The miracle wasn't that the artificial ports worked perfectly. It was that the logistical system was robust enough to survive when they didn't. In the end, the war was won not just by the genius of the engineers who built the ports, but by the adaptability of the quartermasters who kept the supplies moving when the ports sank. The story of the Mulberry harbors remains a defining monument to the scale of industrial warfare. It reminds us that in any high-stakes operation, be it a military campaign or a global supply chain, the most critical asset is never a single piece of technology. It is the ability to adapt when the technology fails. The miracle was not the concrete. It was the capacity to endure the storm.